So a surface of revolution is formed by rotating a curve around a line, a fixed axis. So it could be one of the coordinate axes or it could be a different line. For us now, a surface of revolution, we're only going to consider the case where the axis is either the x-axis or the y-axis. So if we have this curve here and we rotate it around the x-axis, 2 pi radians around. So imagine the x-axis is fixed in space, we're rotating this around, generating some kind of 3D shape. So if we end it here, then we end up with some sort of 3D shape like this. So each cross-section of this shape is well, it looks to be a circle from the picture I've drawn. So if you've ever wondered how you could find the volume of something like a water bottle that's a funny shape, one way is to use this. A different way, of course, would be to fill it with water and then pour the water into a measuring jug or something, but a much more interesting way is to use calculus to find the volume of an object like this. So how are we going to do that then? Well, if we consider breaking this 3D shape up into lots of small little pieces, so if we take a piece like this here, that's some sort of so if we kind of chop this up into lots of little pieces like this, so then if I just draw one of these pieces, so I've got this this piece here I've redrawn here, and if we let the width, if we let this width be delta x, so if you like we can approximate this by cylinder. So this is approximately a cylinder of height delta x. And then what is the radius of this cylinder? Well, this is supposed to be symmetric about the x-axis because that's the axis around which we rotated the curve. So the center lies on the x-axis, center of this. So really this isn't drawn quite right. The x-axis should go through the middle of each of these lines. So the radius is going to be y, because the height up to this point here from the x-axis is y. So we have radius y, width delta x, so the volume of each of these little pieces is, so the volume of a cylinder is the area of the circle, that's pi y squared, times the height, delta x. And then we have infinitely many little pieces like this, so we need to add up. So the volume of the surface enclosed by the surface of revolution is going to be, well, it's the sum of all of these little volumes, but only as we take the limit as delta x goes to 0, because we have all of these little pieces, and as we take the limit as delta x goes to 0, this thing becomes closer and closer to a cylinder as we make delta x smaller and smaller. So we need to take this limit as it goes to 0, and if this x value over here where we started is a, we start when x is a and end when x is b, then we're summing from x going from a to b of pi y squared delta x. And now, if you think back to integration, the limit as delta x goes to 0 of the sum of something with a delta x in the sum, what is this object? It's an integral. This is the integral from a to b of pi y squared dx. So what we've done is we've shown the volume enclosed by this surface of revolution is given by this formula. So this is the volume enclosed by a surface of revolution rotated 360 degrees or 2 pi radians about the x-axis. And analogously, it can be shown that if we instead rotate around the y-axis, the volume will be the integral of pi x squared dy, where the limits are for y, but we'll come on to that later. And this can be used to prove all kinds of volume facts that you've seen previously that maybe you've never proved before. For example, the theorem that the volume of a cone is 1/3 pi r squared h. What is the proof of this theorem? So it's possible to prove this without calculus, but it's quite hard. Probably the easiest way is, well, let's rotate a line around the x-axis to form a cone. So if I draw some axes, and which line could I rotate to form a cone? Well, if I rotate this line here, and we want the radius to be r, that's this height, and we want this length to be the height, h, of the cone, and when I rotate this it will form a 3D shape that's a cone, like so. And then what do I need this line to be? Well, if this is r and this is h, the gradient is the ratio, r over h. So this line is y equals r over h, lots of x. And now let's use this formula. So this is 0, and this limit here is h. So the volume of the cone is the integral, where x goes from 0 to h, of pi times y squared dx. And then what's y? Well, y is r over h times x. So this is pi times r squared x squared over h squared dx. R and h are just constants, and pi is a constant. So we can take all of those outside, and then let's integrate x squared. That will give us x cubed over 3 between 0 and h. If we put in 0, we're not going to get anything, so we just need to put in h. So we have pi r squared over h squared times h cubed over 3. And that is equal to pi r squared h over 3. So we've proved that the volume of a cone is 1/3 pi r squared h. So that's really quite neat. And we could also use this method to prove that the volume of a sphere is 4/3 pi r cubed. So that's going to be on the homework, I think. And yeah, so this method, calculating this integral, is how we find the volume of a surface of revolution when it's rotated around the x-axis.